Hey guys, and welcome back to another video on the channel. In today's video we're going to be trying to evaluate this particular integral. So the integral from 0 to 1 of -1 all to the power of x dx. Now what's so special about this integral is pretty much we're going to get something complex out of here, because if we had x that's smaller than, well, let's say x was a half, you're going to have a square root of -1 in there. So for starters, this function is going to have some complex values. So to answer this question, to even start integrating, we want to try and turn it into pretty much a complex function straight away. So what we're going to use is Euler's identity. So e to the I theta is equal to cos theta plus I sine theta. And we want to somehow get an expression for -1. So if I had theta is equal to, well, let's say pi on 2, that here is going to give me e to the I pi on 2. That's going to give me 0, and that's going to give me I. But if I made it pi, that will give me 0, and that will give me -1, which is what I want, because I want -1 in there. So what I'm going to do is substitute theta for pi. So I'll have e to the I pi cos of pi plus I sine of pi. Okay? So therefore e to the I pi is equal to -1. So that means we can substitute this -1 with e to the I pi. So our integral now becomes this guy here, from 0 to 1 of e to the I pi all to the x. Now the reason we wanted to do this is because integrating e to the x with respect to x, it doesn't change. All it adds is an arbitrary constant. But if it had bounds, like let's say it had a and b, then you'd have to evaluate those bounds as well. So now we've got an expression with Euler's stuff in here. And the cool thing is we can use an index law in here and bring the x down here. So our integral can now be evaluated as this. 0 to 1 of e to the I pi x dx. Right. So what we have is actually this scenario here, where you have some constant out the front here. All we got to do to evaluate this integral is divide by the differential of up here. So the differential of this function here with respect to x will be I pi. And then all you got to do is write the function again. So e to the I pi x, and then your bounds. So from 0 to 1. Okay. Substituting in 1 first, you're going to have e to the I pi times by 1 all over e to the pi, minus substitute of our second bound, so we'll have e to the I pi times by 0 divided by e to the I pi. Right, so what happens over here, that just turns into this, e to the I pi all over I pi, minus that whole thing turns into 1 because e to the power of, because 0 times pi times I will be 0, so e to the power of 0 will be 1, so you have 1 on I pi. And you'll notice that these are common denominators, so we can evaluate this even further. So we'll have e to the I pi minus 1 all over I pi. And we said before that e to the I pi is -1, so we can replace this with -1. So we'll have -1 minus 1 all on I pi. So we'll have -2 on I pi. And if you want, you can leave it like that, but what I'm going to do is make a complex value go on the top. So I'm going to have our answer here, and I'm going to multiply both top and bottom by I. The reason I'm going to do that is because I'm going to get an I squared on the bottom, which will turn to a -1, which will eliminate the complex value on the bottom. So what we have is -2i on I squared, which is -1, so we'll have -1 pi. That cancels, so we have 2I on pi as our answer for our integral. And yeah, we can write it like that, 2I on pi. Yeah, I hope you enjoyed that quick little video. If you want to see any more complicated integrals, just try and leave some in the comments. Yeah, like and subscribe as well.